kinds of creative purposes, personal purposes. And we are super fortunate today to have Ted Moore in from the East Coast, from multiple places on the East Coast. Ted is an amazing intermedia artist, composer, performer. I don't know what other words you use to describe yourself, but he's done all kinds of incredible work, both making art and also kind of building tools to make art. And he's going to be providing a FluCoMa workshop for us today. And so for those who are joining online, please feel free to join in. All of the workshop will be done using Max, and you can download Max 8 and sign up for a free trial. So please do that if you're joining online. I'll let you say how the format is going to work and everything, but I'm super grateful to have you. Please feel free to ask questions, and consider coming back. I'll just say now, the next 2 weeks, next week we're going to be having Caitlin Minji-Ao, who's a sculptor working in glass, who also does video work with machine learning, and she's going to be presenting some new work she's been doing around, her tagline is "Work in Progress with Roombas." So I'm super excited to see what that means. And then the following week we'll have Brian Pardo, who leads the Interactive Audio Lab at Northwestern and develops tools for audio and machine learning. So I'll just say that now. But it's incredible to have Ted here. Super grateful that you came out, and let's welcome Ted.
Thank you. Thanks for having me. It's lovely to be back in Chicago. Nice to see some familiar faces and meet you all. Hello to the internet. So today we're going to do a FluCoMa workshop. We have 2 hours, so we'll do sort of a very common FluCoMa introductory activity, and it'll give you, we're going to train a neural network to do classification, so a very classic machine learning task that's broadly applicable in a lot of ways and could be extended and incorporated into individual artistic projects in many different ways. And then for the second half or so, I have some other things we could do planned. Also, if there are questions about FluCoMa or about how these tools might be expanded or other parts of the toolkit, I'd be glad to do other things too. Happy to swerve as desired. First of all, download this Google Drive folder. It has some patches we'll use. I also put in there the slide deck and some other things, some other patches we probably won't get to, but maybe they'll be useful. I'm going to do a little bit of preamble, and then we'll dive into the patch. So first of all, I'll just talk about what is FluCoMa. It's an acronym for Fluid Corpus Manipulation. I made it with these other colleagues at the University of Huddersfield in the UK. So it was a 5-year project. I only worked on it for one of those years, the last year. And in particular, my role was to build out the pedagogy, the examples, the tutorials, and teach a bunch of workshops. So I've continued doing that. Here I am. So FluCoMa's tagline is that we want to enable techno-fluent musicians to use machine listening and machine learning in your creative practices. And by techno-fluent, I mean if you have come to this workshop, you are a techno-fluent musician. If you are using your computer in any way to make music, then you are part of the target community that we're looking at here. Another tagline for FluCoMa that I've started using very recently, which I don't have on this slide perhaps yet, I should add it, is your data, your sound. It's this idea that it's about the data that you are interested in, the sounds that you make already, training your data and your sounds in machine learning algorithms to generate new outcomes. And this is opposed to, perhaps, using big models made by corporations that live on a cloud somewhere, using other people's data, models designed by researchers, not by you, and so the outputs are perhaps less personal, right? Less idiosyncratic to your artistic practice. FluCoMa is very much about the interests, knowledge, sounds, data of individual artists and individual artist workflows. So that's what we'll do today. So what we tried to do in this project is integrate machine listening and machine learning into Max, SuperCollider, and Pure Data, so all 3 of the major creative coding platforms for musicians and sound artists. We also made a lot of learning resources, tutorials, documentation, examples that you can find on learn.flucoma.org. We might visit that site today as questions arise, and it might be useful to go poke around there. But I encourage you to go check that out. There's, like I said, reference for all the elements in the toolkit. Also, there's a lot of tutorials you can find. There's also a lot of examples of projects that artists have done with FluCoMa with big, extensive write-ups by a person on our team who did sort of a musicological analysis of the toolkit and these projects and wrote about how the artist made them and did some analysis. There's also a bunch of podcasts of him talking with different artists about using FluCoMa or machine learning generally. So it's really a huge repository of stuff to go dig through and find inspiration about or see examples of. It's really worth visiting. And then also we have a discourse where there's a lot of discussion, questions, answers, sharing code, mostly about FluCoMa, but also about other things too, machine learning and electronic music, and it's a nice community, so check it out. Okay. So this is some of the elements of the toolkit. We, of course, will not look at all of this today. I put it all up just sort of as like something to see. Maybe there's some things that you recognize or want to ask about later. But in particular, I'll draw your attention to these headers. So the FluCoMa toolkit is designed into these different sort of categories. There are tools for slicing audio, so analyzing sound through time and finding ways to cut up that audio in time into smaller slices. Ways of decomposing audio, so looking at the spectrum of a sound and finding ways to analyze that spectrum and then break it apart into different sound objects or sound elements spectrally. There's tools for doing audio analysis, common things you'll notice like pitch, loudness, but then also more esoteric analyses like mel bands, mel frequency cupstroke coefficients, things that analyses that are very useful to machine learning algorithms. So we've included that here as to get us towards the rest of the tools here. I'm going to hop over to analyzing data, which is that we have tools for doing all sorts of data science and machine learning. Once we do those analyses, being able to train neural networks, find nearest neighbors, do different clustering algorithms, dimensionality reduction algorithms, ways of organizing data, and then doing something creative with that data. And then lastly, we have some elements for transforming audio. So sort of once we find something out about our audio through analysis, maybe we do some data manipulation and organize our data and our sounds in different ways, then we might do some audio transformations to generate new results. Here's a workflow of sort of how that often plays out in FluCoMa. On the left, as I said, things for slicing up audio in time and decomposing audio spectrally. Then once we sort of find out the sounds that are in our data set of audio, we can do some analysis. Once we have that audio analysis that is describing the sounds as some sort of numerical representation, then we can take those numbers and start doing data science and machine learning with them. And then once we find similarities, combinations, patterns with our machine learning algorithms, we might take those data representations and then do some sort of morphing, synthesis, concatenation with our audio. Today we're really just going to talk about sort of the middle of this diagram. We're going to do some audio analysis and some machine learning. So there's much more to explore after today. And if there are more about this, questions about this we want to look at in the second half, we certainly can. Okay. Any questions about any of that? Observations? Cool. Let's all go to Max. Who here has Max installed? Great. Who here has FluCoMa installed? Great. So here's how we'll install FluCoMa. If you go to Max and go to File, Show Package Manager, you can search for FluCoMa.
May I just
Yeah.
briefly interrupt? If you don't have Max installed, you can find it by Googling or searching Max MSP download, and there should be a trial version for you.
Thank you. And then if you see this nice swirly picture, double click on it and click install. And I think you have to restart Max after you install something in the package manager.
I'm updating the installation.
Nice. I'm also on Max 9.
Yeah, see.
Yeah,
It keeps crashing for me.
Max 9.
Yeah.
Oh no.
And I think we'll be okay if you're on a pretty recent version of FluCoMa, but you might check and see. I'm on 1.0.8, which I can see is the most recent, so updating might be wise, but I don't think there are any major changes that have happened. Great. Okay, so here is the patch that we're going to build first. What we're going to do is we're going to use this collection of multiphonics as and trombone tones as our data set. We're going to do some audio analyses of these sounds using this object MFCC, which stands for Mel Frequency Cepstral Coefficients. It's a type of audio analysis that is very commonly used for timbral distinction or timbral discrimination, so we will use that one here to tell the difference between these two timbres. We'll collect a bunch of data from the oboe multiphonics and the trombone tones, and then we're going to train this neural network to be able to identify or predict, classify these two different instruments based on their timbral analysis. And then we'll be able to play these sounds back in real time, give some real-time audio analysis to the neural network, and it will make a prediction as to whether that sound is a trombone or an oboe. And then afterwards, replacing trombone and oboe sounds with sounds of your choice will be a very wise next step. We'll talk a little bit about how this is actually going to work before we go train it, or before we go build it. So the type of neural network that we're using here is called a multi-layer perceptron. It's sort of a subcategory of neural networks. And we call it a multi-layer perceptron because as neural networks are often built, we have these multiple layers. Here we're looking at a sort of toy example where we have 3 neurons or 3 nodes as our input layer, 2 neurons or 2 nodes as our output layer, and then in the middle we have another layer that we call the hidden layer. In some other larger neural networks we might have more hidden layers, but in this case we'll just have one, and today for the task we are going to be performing, we can probably get away with just having one hidden layer because it's not too complicated of a task. But as we need neural networks to do more complicated tasks, we might need to make the neural network larger so it is able to sort of accomplish more complicated understanding of the input and outputs. The task we're going to perform is called classification. We're going to have the neural network predict which class or category an input belongs to, in this case trombone or oboe. So the way we're going to do this is we're going to take our trombone examples and our oboe examples, but first we'll take all the trombone examples, we're going to do our audio analysis. In this case we're going to do, like I said, MFCC values, but this could be other things too. It could be things like pitch, spectral brightness, spectral noisiness. And we're going to take those audio analyses, we're going to give them to the neural network as input. And then at the same time we're going to be telling the neural network, this example that I'm showing you, this input that I'm showing you, this is an example of a trombone. And we're going to do the same thing with the oboe examples. We'll do the audio analysis, send them as input, tell the neural network this is an example of an oboe. And then the neural network is going to take all of these inputs, feed them in one by one, take them into the neural network, do some internal math that we're going to sort of skip over today. But it does some internal math. It's mostly multiplication and addition. And then it's going to make some output guess. And at first, these output guesses are very wrong because the neural network is initialized using randomization. So the sort of internal parameters that are doing the math, they're basically random values. So it makes that output guess. At first, it gets it quite wrong, but it checks that guess against the thing that I asked it to predict, in this case, an oboe, and it figures out, okay, this wrong guess that I made, how could I adjust myself? How could I adjust the internal math so that the next time I get this input of audio analyses, my guess can be closer to the thing that I'm supposed to predict, the oboe. And it does this with all of the oboe examples, does with all the trombone examples, making all those adjustments. It does this with all of my data many hundreds or thousands of times. And all of those slight adjustments, all of those slight improvements bring us to a result where it should be making guesses that are pretty accurate. And hopefully we'll be getting these guesses that it's making be very close to and very accurate to the outputs that I've asked it to learn. Then what we can do, once it is trained, which is the process I just described, is we can show it an example it's never seen before, right? Hopefully, probably a trombone or an oboe, but that we didn't train it on. Do the same audio analysis, feed that as an input to the neural network, and have it make some output guess. And the output guess will essentially be saying that this new example is most similar to the oboe examples before, or the trombone examples, or whatever, right? So it doesn't know, when it's making its predictions during training, or when it's making its predictions during this mode here when we're making predictions. It doesn't really know whether it's training or making prediction. It's just always making a guess. And in this case, if we're using it with an example it's never seen before, hopefully the training will mean that the guess it's making is accurate, is useful. Okay, let's build it in Max. I'm going to have you actually go to the MLP classifier starter patch, which should look like this. And we'll build it step by step together. And this is because the FluCoMa toolkit has some ways of using objects in Max, in particular buffers and FluCoMa objects like data sets, that it's good to get a little practice with, even if you're familiar with Max. These things are used in different ways, so we'll do it step by step to do that practice. Okay. So.
Is everyone able to get the Max patch open that Ted was referring to? Any questions on?
Where's the starter?
Ooh, it's in that folder.
Okay.
Should be in there. That guy.
I have a question.
Yeah.
So you're probably about to describe the pre-processing that we're going to do,
Mm-hmm.
but well, basically, I'm just wondering what that's going to be. Is it dealing with the tax separately from sustain? It looks like it's about to take the whole sample and sort of digest the whole thing.
Great question. We'll answer that in due time, and then but you've raised a really good point, which is one of the challenges with sound, is that we're often dealing with time, and so like how do we capture time? How do we think about time? It's like an important issue. In this case, we're going to do it naively, and we're going to ignore time.
So you just treat okay, yeah, you'll explain that.
But that's a great point. We'll look at an example later that'll sort of try to account for time in a different way. Okay. And make sure that you see this as a nice dark gray object. If yours is like sort of gray, like light gray or like slightly orange, that would mean that the toolkit is not installed. So we need to check that.
I had to close out of Max and reopen Max, and then it stopped being orange.
Yeah. Okay. So first thing we're going to do is we're going to put in here the audio analysis. So I'm going to type in, make a new object, and I'll type in fluid.mfcc. Fluid is the prefix for all the fluid corpus manipulation objects. And MFCC is the type of audio analysis that I described that we're going to use here. I'm going to put in a number 13. 13 is actually the default, so we could just leave it off, but what I'm specifying here is that I want the MFCC analysis to give me 13 values, and these 13 values taken as one whole set, sometimes we call that a vector of values. These 13 values as a vector are going to be used to describe the timbre of the sound. Any one of these is not particularly useful on its own. When we take them as a collection, they can be very useful in differentiating between timbres. I'm also going to add one more attribute here, at startcof1. And this is because the 13 values that MFCCs give me, they're called coefficients. That's just sort of a math term about how the equation works. But I'm telling this object that I want it to give me 13 values starting at coefficient 1, as opposed to starting at coefficient 0, because in this case we would start counting at 0. And so rather than giving me coefficients 0 through 12, it'll hop over coefficient 1, coefficient 0, and give me coefficients 1 through 13. And this is because coefficient 0 actually really corresponds to the overall energy in the sound, or like how loud the sound is. And so here I don't want to show our neural network information about how loud our sound is. I really just want to give it information about the timbre of our sound. Because I want it to be able to make accurate predictions even if the trombone is playing quiet or loud, if the oboe is playing quiet or loud. So I don't want to have it learn things about loudness. And here we're explicitly removing that information. So I'll feed the audio in here, and we'll see some sounds come out. Bunch of zeros for now. These are oboe multiphonics, so they're noisy. But you can see these values spill out. And some trombone tones. I'm going to, in order to visualize this a little better, I'm going to make an object called a multislider. And if we send our values right into there, it'll just display them as a nice graph. But what we should do is we'll go over to the inspector, and down here we can change the range of our object, of our multislider. I'm going to make it go from like -50 to +50. Now you can see him a little more clearly. So those are the 13 values that we're going to use to do this classification. Okay. So now what I want to do is I want to start collecting some audio analyses into a data set so I can have my data that I'll train the neural network with. We will make a new object down here called a fluid.dataset, tilde.
Is everyone cool with how to create a new object in Max? Cool, great.
And we're going to give it a name. I'll call it my timbre data, because that is what I will put there. Is this big enough? You want it a little bigger? Can you see well? And then we're also going to make an object called a fluid.label set. And this is going to be where we're going to put the labels of our data, whether it is a trombone or an oboe. So we're storing those things separately, but we'll see how we're going to associate those two together so we know which audio analyses correspond to which labels. Yeah.
Just really quick, I just wanted to make sure with the multi-slider, what was the range you set it to again? Was it -15, 15?
-50 to 50.
Oh, 50.
50, yeah.
Just making sure.
That'll capture most of the MFCC values. You can sort of see the shape of it. Okay. And here the label set, we'll give it a name. I'll call it instrument, because that is the categories that we're making. In order to get data into the data set, we first need to get these values into a buffer. Now, usually in Max, when we're using buffers, we're storing audio in there. And very commonly has 44,100 samples per second. So if we have many seconds of audio, it could have hundreds of thousands or millions of samples in it. In this case, because our vector is 13 values, we're just going to put those 13 values in the buffer. That's all we're going to include in there. So we'll make a buffer. We'll call it MFCC buff. And then we can specify right off the bat here, we'll say at samps 13. So it'll be 13 samples long. And then in order to get our values into the buffer, we're going to use this object fluid.list_to_buff, which will receive a list, the list of 13 values, and it'll write them into the buffer. We have to tell list_to_buff a destination, which buffer it should write into, and of course that buffer will be MFCC buff. I'm going to preempt a warning some of you will receive in a moment by putting right in here a defer object. List_to_buff sometimes gets confused about which max thread the data is on, and then it will complain that it's on the wrong thread. And if we put a defer in there, it'll keep things tidy for us. Okay. So now, if I play some sound into here, and we look at this buffer, I can double click on it. We can see, sure enough, there's that data in there. It's only showing us -1 to 1, and it's updating a little slowly because it's just for like inspection purposes. We can see that those values are being written in there. Okay. So now we have that data in our buffer, and we can add it to our data set. I see some people are still typing. Okay. So the way that we are going to get it into the data set is we're going to send a message, add point. And add point is going to take 2 arguments. The first one is going to be an identifier that will uniquely identify this data point in the data set. We're going to construct a collection of objects that will make a pretty looking identifier for us in a moment. For now, I'm going to put in a $1 so that we can pass our identifier to that message, and it will replace the $1 in that message. And then the second argument that add point needs is going to be which buffer contains the data that we want to add to the data set. So this buffer will be MFCC buff. And that message will go into the data set. So whenever that message goes into the data set timbre data, the data set timbre data will go and look at that buffer, MFCC buff, and whatever value is in there at that moment in time, it will add to the data set. So we can see that these values are sort of constantly changing. And so we'll have to think about when to add the data points so that we know what the data is actually in there, right? That's a teaser for what's coming up. Okay, at the same time that we add a data point to our data set, we're also going to add a label to our label set. So we'll say, over here we'll send a message to the label set, add label. And add label is going to take 2 arguments as well. The first one is going to be an identifier that identifies this label in the label set. We're going to do the same thing, we'll pass that in. And then also the actual label, so what the instrument is, whether it's trombone or oboe. We're going to build a way to pass that in a moment as well, so we're going to put a $2 there. So we're going to construct all of that information together. And that'll go into the label set. Okay. So now let's build this identifier. I'm going to start with a bang, or a button, I guess we call it. Add points, or add data point. And then I'm going to use a counter so that each time I hit the button, it'll give me a unique integer, just as a way to have a unique element to our identifier, so they always are different. And then I'm going to use this object combine, and I'm going to say example dash I. Okay, and then at triggers 1. So what combine is going to do, it's going to combine these 2 things together for me, example dash and the I. I'm going to replace that I with my integer so that it'll be like example 1, example 2, example 3. And those will be the identifiers that we use to add the data points to the data set and the labels to the label set. At triggers 1 specifies that the first inlet, this one here, as opposed to the 0th inlet, specifies that the first inlet be a hot inlet so that it'll output a value for me, and this inlet is for example dash, and this inlet is for the I. So I want to send my integer to that inlet, and it'll give me an output identifier. Now every time I hit that button, I get example dash and a new integer, so that all of my identifiers will be unique. Okay, so now we can take that identifier, we can pass it right into our add point message. That will start adding data to our data set. But first we need to still combine our identifier here with the label of the instrument that we are using. The way I'm going to do that is I'm going to use a join object. To join together these two pieces of information. Here, the $2, this second piece of information here, I'm going to make either the word oboe or the word trombone. And I can put that into my cold inlet of my join so that every time an identifier comes into my hot inlet of join, it'll grab the label oboe or trombone, combine them together, and then it'll move on to add label, and we'll have add label, the identifier, and then whichever instrument I most recently clicked on here. So let's try to do that. So the way we'll do this training is I'll start with the oboe multiphonic. So I'm going to hit oboe. So I've stored oboe into this join object here. And then I'm going to start playing oboe multiphonics and clicking add data point. I'll add a couple here. I'm just clicking like once a second or so. And now we can see if those got added in. I'll send a print message to both my data set and my label set. And now we can see in my data set called timbre data, I have 5 data points. Points 5, columns 13. That's good because we have the 13, I guess it's over there. We have the 13 MCC values that we're using as our analysis vector. And we can see some of the data there with some ellipses in between. And we can see that the identifiers for those data points range from example 23 to example 27. And then in my label set, I also have 5 points, 5 labels here. And those also range from example 23 to example 27. So this is how, when we train the neural network, it's going to know which audio analyses correspond to which instrument label. They're going to share that same identifier.
We're getting a question on the online chat, so
Awesome.
I'm just going to say aloud in case anyone is less familiar with Max that if you're not getting sound to play, that could be because your audio is turned off within the patch, in which case you will want to go down to the lower left where that little speaker icon is and click on it so that it is highlighted.
And if you want to specify where the audio should be routed to, options audio status will let you change that. Okay. So I added 5 points during this first oboe multiphonic. I'm going to start there and start adding some more oboe multiphonic data points. So make sure oboe is clicked in here and then add some points. Now you'll notice I'm going to not click add data point during the silence in between the multiphonics, because that would not be an example of a multiphonic, right? That would be an example of silence. So I don't want to accidentally label an analysis that is of silence the wrong thing. Okay. And I'm going to stop there and just train or just make data points from these first 5 multiphonics. So this is going to be our training set. Our MFCC analyses from these multiphonics is what we will train the neural network on. And I'll keep these 3 as examples that it hasn't been trained on. It has not seen MFCC analyses from those multiphonics. So we can test it on those later and see if it actually can identify those as well. I'll do the same thing with the trombone tones. So I'll only train on these. I'll only add data on these tones, and then we'll save the last third or so for testing on. So now I will play some trombone tones. I'll make sure to hit trombone here so that it stores trombone in there, and we'll start adding the word trombone as our label. And I will hit play and add some points. Again, skipping over the silent bits and stopping there. Okay. Now if we print, we can see we have identifiers that range from 23 to 103. Looks like we have 81 data points. And we can see some of them here at the beginning when I was adding them were called oboe, and some of the ones here at the end that I was adding are labeled trombone. So that'll be the data that we'll use to train it. Let's all make some data, if you haven't already. Make some trombone and oboe data points and labels. Feel free to make sound into the room. It is okay. We will all listen.
Weston's going to be in Chicago soon.
What?
Weston is going to be in Chicago soon.
Nice. What for?
There's a venue downtown called the Graham Foundation. He's doing a duo with somebody.
Cool. I'm sorry, I will miss that show.
I just says because he's the trombonist in the track.
That's very true. That is what Dale Lenke stands for there.
Would you say that there's a certain threshold of points we should be hitting within the data set?
So, not really. I added about 1 every second or so. I mean, I have about 80 points. That'll definitely be sufficient for this task. Depending on the task, you might need more or less data depending on how complex the task is you're having the neural network learn. For this task, it's pretty straightforward, so we're going to be safe even if we have fewer points or more points. The thing that sometimes trips up people in this training in this patch is that they accidentally have some points that are mislabeled, either because they accidentally mislabeled them or because they were pressing during the silence, and so the neural network will be confused. Yeah. Okay, so now that we have this data, we can train this neural network. I've put in some attributes here that are going to work well for us. We're not going to talk about these attributes today because it is a whole another sort of activity of talking about them. However, I will orient you to the learn.flucoma.org page, which has some good reference for the neural networks. One page is called Neural Network Parameters, and it goes through all of the attributes in the MLP classifier that we're using here to do classification. So the hidden layers, activation functions, learning rate, validation, etc. So I encourage you to go check that out. So this fluid.mlp classifier, MLP again stands for multi-layer perceptron, sort of a type of neural network. Classifier is because classification is the task we are doing. There's also the fluid.mlp regressor, which is the same structure of neural network, the multi-layer perceptron, but is for a different task. It's for performing regression, and we'll look at that one in a little bit. So in order to train this, we're going to send it a message fit. And fit here is synonymous with train. It's like line of best fit or fitting a curve to data. This is sort of terminology. And we're going to give fit 2 arguments. The first is going to be the inputs to the neural network, which is going to be all of the data points in the data set called timbre data. So we're going to tell it timbre data is where you'll find the inputs to use. And the second argument is going to be the outputs. So it should be the label set that has the labels that it will try to predict as the output. And that label set is called instrument. Now before I hit that message there, I'm going to grab the outputs because it's going to give us some information that will be useful. And if I send in this message, it reports to me fit 0.08. So the fit here is just saying fit back to me. So I said fit, it says fit, we're all on the same page. That's sort of what it is telling me. So this number is actually not called the fit number, even though people often describe it or say it because it looks that way. So this number is called the error or the loss. And it is a representation of how inaccurate the neural network is yet at doing the task I asked it to perform. So because it is the error, right, it is how inaccurate it is, lower is better. Lower means more accuracy. There's no real objective way that we can talk about this number, like, oh, if it's below 0.08, then we know it'll be good for... We can't really talk about it that way because different neural networks, different data will have different errors that it'll provide. However, what we can do is we can watch how this number changes over time and see if it goes down. And if we see it going down over more and more training, we can say that yes, the neural network is improving, it is getting better and better and better, and so we know it must be learning from the data. And once it has done a lot of learning and we've seen it do that improvement, then we can say, okay, it probably has learned to do this task, and then we can test it and see how it's doing. So I'll hit fit again and we'll see what happens. 0.02, so it went down by about 60%. That's pretty good. So it has gotten better.
If it goes up.
If it goes up, then you should keep training and see what happens.
Alright.
Sometimes these things, they'll like get a little better, get a little worse. And this is the neural network trying to figure out what to do. Sometimes eventually it'll get,
I see.
and then it'll get even better after that. So sometimes you just got to train for a little bit.
Is there a way to clear the data point that I previously tried?
Clear the neural network or the...
Yes, the previous. Yes.
So for most FluCoMa objects, you can send it a clear message, and it'll clear the whole thing. You can send a message, I think it's like delete point. Yeah. And if you pass in an identifier there, whatever that is, it'll delete that point from the data set or the label from the label set. Probably delete label is the label for the label set. And clear, of course, would clear the whole thing. So I'll hit it again. It went down again. This is good. I'll just hit it a bunch and see that, sure enough, it has gone down quite a lot. At this point, a few orders of magnitude from where it started, so we can feel pretty confident that it has learned quite a lot, right? It has improved. It has learned from the data that I'm showing you. Train it, see how it goes. Yes?
I got an error that says sizes do not match, which seems like I screwed something up pretty fundamental.
So my first guess is check for a typo.
Yeah.
Like,
I had that originally, and then I fixed that.
great. In
but
that case,
did that propagate?
yeah, so then clear the neural network
Yeah.
and then try again. Because if that typo gets in there, then it'll like, could be.
Screw things
yeah.
up, sure.
Who has a loss that they want to share with us?
A loss?
I mean an error, a loss measure.
We're getting personal now.
What is the number on your screen?
0.0374.
Nice. I'm guessing it went down quite a lot to get there.
Yeah.
Cool. Is yours working now?
I'm about to try it again. Here. Yeah.
Cool, great.
Thanks. Yeah.
So because we're all using the same data and the same neural network structure here, in this case we can sort of compare losses with each other because it's essentially the same task. But if we were to change the sound or change some of these parameters in the neural network, that's when we would need to not try to say objective things about our loss. Okay, so once it is learned, we can then have it make a prediction. The way we will do that is we will send it a message, predict point, and predict point is going to need the name of a buffer that it should go to and look to see, find some MFCC values to then feed as input to the neural network, right? So we need to have some audio analysis to feed in, and then it will make a prediction from those values. So since we're already writing our MFCC analyses into the buffer called MFCC buff, we'll just use that buffer. And then, if I send it that message, it will go look at MFCC buff, take those 13 values, feed them as the input to the neural network, make a prediction, and then report back to me what that prediction is. Predict point again here is just, so I hit the message. Predict point here again is just saying I did that thing you asked me to do, and then the prediction it makes is oboe. Now of course there isn't an oboe playing right now, it is silence, but this is because we've only trained the neural network to have any conception of oboe or trombone, right? It doesn't have any knowledge of what silence is. The only predictions it can make are the predictions that we trained it on. So it thinks this silence is oboe. We'll see a way of sort of maneuvering around that in a moment. What we can do now is play some sound and then hit predict point and see what it tells us. Let me actually start back here at the beginning. It thinks that is a trombone. So you got a little confused in the silent bit there because it doesn't know what. I didn't train it on any silence. Let's try some oboe sounds. Sure enough, it thinks that is an oboe. So of course, these sounds here are the sounds that we trained it on, so one would hope that it would get those correct. But here are the ones that we didn't train it on, so let's try it on these and see how it does. Sure enough, it thinks that is an oboe. Multiphonics, it gets them correct oboe. Wait, what did I say last time? Trombone? Yeah. Okay, so now the neural network is trained in making accurate predictions. This is a small data set, but of course, you know, the idea here is we would scale it up or find use cases for these predictions about things we might do with them. See if yours makes accurate predictions. Do the training, do the predicting.
This might be a silly question, but when you're training it on the sound,
Mm-hmm.
what order should you be clicking the label, then clicking the bang for it to associate it with that specific label?
When you're adding the data points?
Yes.
So the way that I've built the patch here is that you really just click one of these one time. So like, you know, click the oboe and then go play the oboe sounds and you can just click add data point as many times as you want because this oboe is stored in here. Then before you go on to adding the trombone sounds, you'll need to click trombone, right, and then go play trombone sounds and click add point.
I'm just going to point this out because there's one person following along online who is less familiar with Macs. You did include in your download folder the completed patch in case anyone got caught at any point in this.
Nice.
So if you feel like you're 3 steps behind and you're not sure how to catch up, there is the complete patch in there, and you can just go ahead and play with it there.
Totally.
You can also
Thank you.
download the entire folder, so you
Yeah.
have the sounds with it too.
Correct.
The sounds actually come with the FluCoMa toolkit. That's where they are. So just in case somebody's looking in that folder, they won't see sounds. Yes, are you making predictions and are they accurate? Great. Okay. So a few points to make out. So remind me your name?
Cameron.
Cameron.
Yeah.
Okay. So Cameron asked, what is the data point here? How are we accounting for time? Or that was sort of the question you asked about. So here, because we're clicking add point at given moments when that sound is playing, we're really just using a single slice in time as our analysis vector that represents those labels. It is, for those who might be curious, it is a single FFT frame, right? We're taking an FFT of this, an FFT of the sound, and then doing our MCC analysis from that. So that's where those 13 values are coming from. Now this will work well for these sounds because they're just sort of static timbres, right? We're sustaining something, so any slice of that will be pretty representative. But if we had a sound where the sound is changing a lot, like maybe a drum hit, which will have an attack, some sort of decay, usually some sort of transformation that happens over the course of that time, then we'll have to think a little bit more about how we want to do that. We'll see a patch in a moment. We won't really dig into it, but I'll give you a teaser of how that's usually done with FluCoMa, is that we can analyze a duration of a buffer or a duration of, I guess it would be in a buffer. We analyze the duration of some buffer, and we can get 13 MFCC values for sort of all of the moments in that buffer, basically all of the FFT frames in that buffer. And then often what we'll do is we'll just take the average across time. So if we have 13 MFCCs, we'll take what is the average coefficient 1 across that sound slice? What is the average of coefficient 2 across that sound slice, etc. Sort of like taking the average pitch across some sound slice to summarize the pitch information of that sound. And that way, if we have some sound slices that are 1 second and some sound slices that are 750 milliseconds, because we're summarizing them using the average, we can compare apples to apples, right? We just have like a single value or a single vector that's the same size to compare the two, or to train the neural network on. We also could take the maximum value or the median value or some other statistical analyses as well. So there's an object called fluid buff stats, which will do that statistical summary of our analyses. So check that out. I can show you where that is in the next patch, but that we won't get to sort of using it today. Buff stats also can do like the derivative of something. So if we have a sound like a snare hit, and maybe we are going to use the loudness, and the snare hit goes, right? The loudness starts big and goes down, and so the derivative will be a lot of negative values because that loudness is going down over time. So that might be useful for knowing something about comparing sounds, right? So thinking about what is the thing happening over the duration of my sound, over that time that I care about, think about how to represent that statistically or in numbers is a very important and common task when using these FluCoMa tools. Is that sort of a useful answer?
Yeah.
Fluid buff stats is the thing to check out. Okay. Yes. There's one more thing I was. Oh yeah. So another thing we can do is let's just sort of flesh this out a little bit. So the way I might want to use this in like a real application or performance or something is I probably just want to be making predictions all the time. I just want to know like what's the sound, right? So I would use a Q metro, sending out a bang every 50 milliseconds, maybe that's enough, 20 times a second. And just have it constantly be making predictions. So that if I press play on this, we get trombone. If I press play on this, we get oboe. And I can just always know what it's hearing because it's just constantly making those predictions. you can see that while we're playing at silence, it is predicting oboe. Maybe I want it to not make predictions right now because there is not an oboe playing or a trombone playing. So one thing we could do, well, maybe we train it to predict silence, or we have it learn something about silence. One could conceivably do that. However, we have a different tool that doesn't need machine learning that can tell us if something is silent, right? And we can just use a loudness analysis. So we'll just use the fluid.loudness here to give us a loudness analysis. I'm going to add an attribute here at select. I'm going to pass in an argument and just for select in just a moment. But many of the FluCoMa objects can give us a set of analyses. So fluid.loudness can give us both the loudness, which is like an RMS loudness analysis, and fluid.loudness can also give us a true peak analysis, which is a sort of loudness analysis that's often used in mixing and mastering for thinking about loudness slightly differently. In this case, I don't want the true peak, I just want the normal loudness analysis. So I'm actually going to tell it at select loudness, and it will just give me that normal loudness analysis and not give me the true peak. So it's a way we can ask the FluCoMa objects to give us just some subset of the analyses that they might offer. So now if I put this into here, and let's just see what's going on here. So if I play some sounds, looks like that's hovering around negative 20 decibels. So maybe I just want to ask, is the sound greater than negative 50 decibels? And if so, turn on the Q metro. So now I'm having the neural network only make predictions when the sound is above a certain loudness threshold. Pretty useful way of using this classifier. Questions about that patch?
What if one presses play and gets the message wrong point size?
Were you making accurate predictions?
This is asking for someone online.
Oh yeah, great. So then what you should do is try clearing the neural network. Two things. Clear the neural network and train it again. And check for a typo, in particular in your predict point message. You might have the wrong buffer name there. Or check and see if your buffer if you changed the buffer size. Because what it's saying is this buffer that it's trying to make a prediction from is not the same size as the data that it was trained on. So,
Thank you. So now when I click play, the toggle should be on, right?
yeah.
But mine is not.
Uh-oh. Oh, you gotta pass that on.
Oh, I'm not.
Kind of like plateauing.
Well, no, as far as the prediction. Oh, the fit. Fit. I'm getting basically it's jumped on all the time.
No, yeah, I was having an issue.
Is that? Oh, you said it. Yeah.
So yours is saying trombone for everything.
Yeah, but the number is slightly going down, but again, I couldn't follow, I'm not sure how much.
Yeah, I've like cleared it twice and retrained it, and I can't get past like 0.5 on the fit number for some reason.
So when that happens, usually, are you making sure that you have both oboe and trombone examples?
Yes.
Okay,
Yeah.
cool.
Click oboe.
Yeah.
Should the oboe be playing? Should that sound be playing before you click oboe?
Nope, you can just press oboe and then play the sound.
Okay, yeah, I feel like I keep doing the order of operations correct, but the number is just not.
Oh,
it's not
interesting.
getting
What is
right.
it stuck at?
It's getting stuck around like 0.5.
Yeah, that's
I'm
pretty common. So
Okay.
that usually means that the data is sort of inaccurate in some way. So I would try doing it again.
Okay, for sure.
Another thing you can try is just, if it's getting stuck like that, just try clearing the neural network.
Yeah, I've like started from scratch a couple times.
Sometimes what I'll do is I'll send a Q metro into the fit and just let it train like this.
Mm.
And then every so often I'll just clear it and see if sometimes it'll like sort of shake itself out of a rut. Like right here, it's stuck at like 0.18, and now it's like, you know, burrowing down into that solution again. So, yeah.
It still doesn't work.
And while we're troubleshooting this, does anyone have any basic max questions also? Because I know we're all kind of at different places with that.
Greater than -50 looks pretty good, right?
Does it need a float?
I don't think so. I don't think I did the float, did I?
But yours has muted.
We'll email.
You don't need to be Snoopy, but I saw your
We'll email
Are
Cycling
you
74.
cool on the FluCoMa package installation?
Is there an inverse to the MFCC?
I feel like, because, okay, so the orange.
There is
Or are there a
not.
bunch of different?
On all the
parameters
fluid
that
dot
map to
content,
say-
it probably
Like
means that
5 on the
FluCoMa is
fifth
also.
So there's not an inverse because it's essentially a lossy process, right? So because we're taking a whole spectrum, a whole FFT set of magnitudes, and basically compressing it into just 13 numbers, right? So there's got to be some lossy process there.
Yeah.
There is an inverse process you can do, but it'll come back, let's say, blurry. because it's lossy. However, that inverse process is not made available in FluCoMa because of that reason. Because it's not going to be particularly useful. But if you use,
I wanted to know.
yeah, you should do it. So if you go to if you go here and go to MFCCs,
I was joking.
you'll find some information about how they work, including a little demo here where it sort of talks through like what they're doing, and you'll sort of understand, you know, and also it, you can send me an email too because I made this demo, so it's like if you're like
Yeah, just sort of the possibilities of that, like
Totally.
synthesis within that.
totally. Also, you might so if you're familiar with Python, there's a Python library called Librosa that'll do MFCCs. And I don't know if it'll do an inverse for you, but you might be able to get up the data there and use it in a way that'll be a little more under the hood, right, than FluCoMa is. So, yes, it's a good question and a cool idea. It's yes. Okay. So this is our classifier example. Concluded. Of course, I encourage you to put your own sounds in here, right, and see how it works. And you know, yes, use it creatively. I'm going to move on and do. I'm going to show you another neural network example. We won't build it together. I'll just sort of show you the patch and demonstrate it. It'll all look very familiar, so you'll be able to take it from there and investigate it further. So go and open up the regressor complete, MLP regressor complete patch. Okay. So what you'll see here is a chaotic synthesizer that was made by a colleague of mine. And you can hear it's like a noisy, crunchy synth that I know some of us are very familiar with. And so it has these 10 control parameters. And here in this multi-slider, those 10 values are just in the range between 0 and 1. In here, they get scaled up to, you know, being in the range of frequencies or loudnesses, so they sort of get mapped accordingly down in this patcher. But here they're just in the range of 0 to 1, so that we don't really know what they're controlling. Here we're going to use this fluid.mlp regressor to predict those 10 values, 10 synthesis parameters to control that synthesizer with. Those are going to be our output values that it is predicting. Our input values are going to be a vector of just 2 values in XY position on this 2D square. And so we're going to build in this case, data set of input points called XY data, XY positions, and a data set of output points, in this case called synthesis parameters. You'll see there's no label set here because we're working with data in, data out, as opposed to data in, labels out. And just like we did before, we're going to make sure that there's a shared identifier between our input and outputs that we're asking it to learn. We're going to make two data sets that pair an output set of synthesizer values with an input point in 2D space. And we'll do 5 or so input-output pairs of synthesizer parameters, XY position, synthesizer parameter, XY position, synthesizer parameter, XY position. And the neural network will be trained to understand the relationship between those input and output spaces so that if we give it an XY position, it will predict the synthesizer parameters that I asked it to learn to predict from that XY position. The nice thing about this is then that once it is trained, of course I could kind of recall my synthesizer presets or values, synthesis values, that it learns to predict, but also as I move around in this 2D space, I can make predictions using any XY point, and it'll predict synthesis values for that XY position. So I'll do a training example, and then you'll all do it right after that. So here what I'm going to do is I'm going to choose some points, make some data here. I'll choose a set of synthesis parameters that I like. Maybe I want to use this sound. So there's my synthesis parameters. They're written into this buffer called params buff there. And I'm going to pair it with an XY position. So maybe I'll put this sound right there. It's up to me. I can put it wherever I want. And then I'll click add data points. This will all look rather familiar. And now I can see that I was getting an input tap. Oh yeah, that's because I was probably making predictions that whole time, even when I wasn't trying to. And so now I can see that my data set called synthparams has 1 point in it, 10 values, these 10 values here. The identifier is called example 0, and my XY data has also example 0 with an X position and a Y position. So I'll do this for a few more points. Choose synthesizer sound, choose a position, add points. Sound, position, add points. Here I'll do one more. That one in the middle. Okay. And now I can train on this, and we can see how my fit changes. So here's my error. 0.27, 0.29, oh, it went up a little bit. 0.22, 0.15, okay, good, it's going down now. Turn on the Q metro. We'll see it has gone down quite a lot, many orders of magnitude. And so now I can use it to make predictions. I have to reconnect this predict point message, and we should be getting some points that are predicted. And now we see them controlling the synthesis parameters. Okay. Yes. So now you do the same, create some data, train it, and move it around. If you want to, when you're making the data points, if you delete this cable right here, it won't give you that input tap too large error. So you can delete that and then reconnect it.
locked. Yeah, it should be locked actually. If you're messing with this one, give that a try. Yeah. Yeah.
So after you add the decomposition with the synth orientation and then the data points, you make too much way to train it?
Mhm.
Okay.
How many did you make? Like, how many data points did you make? 5?
5.
Yeah, that's great. And you should see the loss go down.
It's hovering around 0.25.
Mine did that too, where it I made 5 points and then I trained it and it decreased and then it just kind of hovered around that
Yeah.
it still worked, it seems.
So one thing that you'll find is it'll always make predictions, because even if it's trained, let's say, poorly or something, it'll still output some values. But usually in this patch, if it's not getting down too low, it's often because the data is such that the neural network gets confused. One common problem is that this point is in the same spot for a number of data points. And so when the neural network is training, it takes this as an input and then says, okay, I'm trying to predict this, and it move over there.
Right.
But then the next data point it gets, this is still the input, but now it's trying to predict something totally different. And so it tries to go, okay, well, I guess I have to go over here, right? And it sort of moves back and forth between those two data points, and it'll get confused and not be able to make as accurate predictions as it could. Basically because you're asking it to predict totally different outputs from the same input.
Right.
And that'll be not possible.
So after I train it, I try using the slider to change the colors.
Mhm.
It doesn't work.
Let me see.
Sure. So I gave it 5 points, and then move it around. Oh, okay, got it.
That's our predict point method thing to make those predictions.
There it goes. Okay, thank you.
Mine is not making any sound, but I think it's I think I have an issue going on with my, there it is.
Sounds like music.
Cool. Okay. So these are the two types of neural networks we have in FluCoMa, the MLP classifier, the MLP regressor. And I hope you can see how it really allows or relies on you to be using your own data, your own sounds, your own synthesis algorithm, of course. Replacing this would be an interesting thing to do with this patch. Changing the input space might be interesting. Rather than using 2 inputs, you could use multiple inputs, maybe XYZ of an accelerometer, or maybe some sort of wearable, knowing something about a body position, or even like an audio analysis, right? Taking some sound, doing an analysis, and then predicting synthesis parameters from the audio analysis, perhaps. Yes. So I think with the last half an hour, it would be fun to show you guys one more sort of different part of the toolkit. That's a change of gears. That's a part I really like. So before we do that, are there any thoughts, questions about these neural networks?
Sure, yeah.
Yeah.
Because I'm just curious how, obviously this is, like you said, a smaller amount of data than we think of neural networks usually needing or using. Without maybe getting into the guts, were there some tricks used to kind of optimize the training so that it can deal with the smaller data, or is it just that we're doing something different, obviously, than OpenAI is doing neural nets?
Yeah, I mean, no, there's no tricks. The answer is just that the algorithm that neural networks are, how the algorithm for their training and making predictions. It's a pretty simple algorithm. The power of, let's say, those more impressive or larger models or corporate applications tends to be in their scale. At least that's sort of the working hypothesis right now. It's about the scaling up that's going on. But applying it on smaller data, we can do it with a smaller neural network. So it's really the same process. It's just an issue of scale, or a question of scale. Part of the FluCoMa thing that I'm talking about, right, is that as one human, as one artist, it's not really possible for me to make too much data, at least not the amount that those massive models are trained on. So, if I want to use my own data and I want to use my own sounds, this is like the appropriate size neural network for that.
Yeah, thanks.
Yeah.
That's good.
Also, the architecture here is that MLP architecture, the multi-layer perceptron, which is in many ways the sort of most basic, generally applicable workhorse of neural networks, right? It's going to be quite useful in many different applications. So it's the one that we've provided here. Many of the larger models that we think about, they're actually using more complex architectures like transformers or convolutional neural networks for the image stuff. So the tricks are actually maybe on that end of the scale, having to think about architectures in different ways to be able to handle larger data. It's maybe one way to answer.
Yeah, makes sense.
Yeah. Other questions? Any questions from the internet? No questions. Okay. So the next thing that I think would be fun to look at is the O3 NMF patch. So NMF stands for non-negative matrix factorization. That's the name of the actual algorithm that's happening here. And what we're going to do is we're going to take this mono drum loop and we're going to give it to this object fluid.buffNMF. And we're going to tell it some things. So we're telling it the source here is our drum loop. We're going to ask it to find two components in this buffer, this sound file that we have, this buffer that we have. That's essentially all the information that we're telling it, just the number 2. I want you to analyze this buffer and try to split it into two different things. That's what we mean here by components. When we do that, we can hear what it has divided out into now two different buffers, or two different channels of the buffer. Here we have the snare. And we have the kick and the hi-hat. And so it's able to differentiate like those sound objects in the buffer, split them apart both in time but also spectrally, right? And write them into two different buffers for us. And we didn't tell it that it was drums. We didn't tell it that something would be like a low sound or a high sound. All we did was tell it the number 2. That's the thing that I think we want you to find. So now let's try with saying 3, and we'll see what happens. Now we can make a guess, right? What do we think will happen? Probably can imagine what those 3 might be. We'll see what happens. The kick, cymbal, and the snare. Now, it doesn't always do it that cleanly. Sometimes it will do weird things where it'll put like the smack of the snare in one, the ring of the snare in another, and then again the kick and cymbal in a third. And this is because, like many of these machine learning algorithms, the way buffNMF is initialized is using some elements of randomness, starting it in a random position, and then from there iterating on some process to try and find a good solution. If that happens, the thing to do with NMF is to just try it again and it'll start initially randomized again, and then it might find a solution that's more, applicable, or what you were looking for, what you were hoping for. So the way this is working, we'll listen to the rest of this in a moment, but first we'll just go look at. Yes, okay. So the way this is happening is we're starting with an STFT spectrogram of magnitudes, by which I mean we analyze the sound file, and we can look at it in these sort of 2 dimensions here, where we have time on the x-axis, frequency on the y-axis, and then the brightness of the pixel is the sort of loudness or the energy of the sound. So we can see here are the kicks happening spaced out in time, low in the frequency spectrum. Here in the middle is going to be the snare drum hits, here and here and here, here. We can actually see the ring of the snare, right? That's sort of the resonance of the snare ringing out in these horizontal lines. And then at the top we have the cymbal energy here, the higher frequency cymbals occurring up here through time. So yeah, here they are sort of graphed out, and we can see there's a lot of overlap. So we would know that we couldn't really try to slice them up into sound slices, because there's a lot of moments where, in particular, the kick and the cymbal are happening at the same time. And of course, the snare rings out for a certain amount of time, so that's going to overlap with a lot of other sounds in time. And we also know that we probably can't use like filters to try to separate these out, because even the kick has energy happening really high up in the spectrum with the smack of the kick drum, and the snare is going to resonate very high with the noisiness of the buzz up there with the cymbal. So there's no specific time or frequency tool that would do as clean of a job separating them as NMF does. So what NMF tries to do is it tries to find spectral templates, we call them, that it can use to sort of resynthesize this whole buffer. And the number of templates it tries to find is the number that we tell it. So in the case of 3, it's going to try to find 3 spectral templates that it can use to describe a lot of the things it will see in this buffer. The way it does that is it looks through and it tries to find, for all of these different moments in time, all of these different spectra, what sort of energies tend to happen together. So for example, like this ringing out of the snare, it tends to happen also with this energy happening, and this one, and these ones, right? We see that happen often together. And so it knows, okay, if I make a spectral template that has, this energy and this energy and this energy, I can use that template to describe a lot of the things I will see. For another one, it might say, well, if I, this sort of energy, all of this down here, that all happens together. So if I make another spectral template that has all of this energy always happening together, that would be helpful in describing a lot of the things that it will find in the buffer. And then, of course, another one for the cymbals. And so once it finds those spectral templates, it is then able to use those as a sort of resynthesis process to recreate what we then end up hearing as those 3 different buffer channels with those isolated, let's say, spectra objects, sound objects, based on the spectral templates that it determined. So that's sort of the resynthesis process. That's what we were just hearing. It also can give us access to those spectral templates themselves, which could be interesting to use in different ways. So here are the 3 spectral templates. We also call them bases. It's how we can address them in the algorithm itself, where we're seeing those spectra. Of course, here is the kick with that low energy. The snare, we can see the sort of resonance of that snare drum. And then the cymbal with all that high energy noise. When it does this analysis, it gives us the bases. It also gives us what are called activations, which is sort of how active, how present is each of the spectral templates for all the moments in time of our original buffer. So here we can see, here are where all those kick drums happen. So here's where all the snare drums happen. And here's how present all of the cymbal energy is through time. in order to resynthesize those different components that we heard, what it does is it takes the basis of, the kick drum in this case, and recombines it with the activation of the kick drum. Using those two together is able to sort of resynthesize just the kick drum parts of the original buffer. Then it does the same thing with the snare basis and activation, same thing with the cymbal basis and activation, and essentially resynthesizes those elements from the original, and then we can hear them separated out. The process is a little more complicated than that. There's some clever sort of processing of the original signal that happens, and it's really cool, but I'm not going to explain it all right now. Just sort of trying to not, the thing about teaching, how much do you lie versus reveal. So you can find some information. I'll point you to a YouTube video you can watch where you can learn more about how the actual happens under the hood, because it's cool. Okay. So once we get those activations and bases, we can actually use them in Max independently. So here we divide it into 3 components. Now what we can do is take those activations and actually just play them back as like a control signal. So here I'm going to send in some pink noise, and I'm going to envelope the loudness of that pink noise through time using these different activations. So that could be useful for, here I'm just using pink noise. You can all be much more creative than that. But that could be useful for some sort of creative application. Another thing is I could use this object called fluid NMF filter, which is we're going to provide it a set of bases. Remember, those are the spectral templates. And then it's going to filter an incoming signal based on those spectral templates. And so we can think of it sort of like a vocoder, where we're going to have an input source signal. It's going to be spectrally modified in some way, and we'll get the resulting filtered output. This is the pink noise again, being filtered by the kick basis, by the cymbal basis, and by the snare basis. Pink noise, there's something. But what we could also do is we could sort of mismatch them in some way. So again, still pink noise, but if I were to use activation 1 and basis 1, that's going to be the kick activation and kick basis. The hi-hat activation and hi-hat basis. But now I could use the basis of the kick, but the activation of the hi-hat. Or another mismatching of the two, the basis of the snare, but the activation of the hi-hat, etc. Or, if we put all of them together accurately matched, we're getting this sort of like pink noise recreation of the original drum kit. But of course, we can mismatch them as well. Sort of loudness and filtering recreation of the original. And again, pink noise is a demonstration tool. You can find more creative applications of it. Okay. NMF. Yes.
Sorry, can you repeat, using the basis as a filter, what was going on there with pink noise?
So, well, actually, we're doing it right here also, I suppose. So with NMF filter, we're giving it the bases, and here we're giving it this information, right? So what are those spectral templates that it used, that it found? And then when we pass in any signal, in this case pink noise, it sort of uses these spectral templates as a filter, so that rather than passing through the pink noise unchanged, which is sort of just would be like loudness everywhere, right? It filters it to only let pass through, loudness here, and not pass through energy down here, or only pass through energy in the low register where the kick is, but not pass energy up higher. And so it's acting as the sort of spectral filter, the filter being the shape of that spectral template.
So it's approximating the spectrum of the other sounds using pink noise as its input.
Totally.
Okay.
And in this case, pink noise is just for demonstration, but it can do anything. Yeah, so, yes. Other questions about NMF? Paul? Paul?
Oh, Bill.
Bill, sorry.
Yeah.
I know you were using NMF prior to coming today.
Yeah.
Is this helpful, or other questions
this
based
is
on
very
your
helpful.
experience
And the
using it?
movie Also, is very helpful. I think the question in my mind is, well, there's two. One has to do with when you have spectral overlap, but not all the time.
Mm-hmm.
It's not like you have
Mm-hmm.
a couple of instruments locked in. What are some do's and don'ts or rules of thumb for trying to improve
Mm-hmm.
separation, or for choosing better separations?
Yeah.
In some flow.
Totally. So that's a great question. So one challenge that you'll often find when using NMF is that because it's just looking for things that happen together, if you have let's say two instruments that are playing a melody together, right? It's going to look through the spectrum and it's going to find that stuff just together all the time. So it's going to put that into one template, right? It will not separate the two instruments. So what you might need to find is, a place where the instruments are playing separately and they're playing together, so it can get a sense of what those differences are. Actually, another important thing to notice is that because it's doing this template making on basically raw FFT magnitudes, if an instrument changes pitch, it probably won't work well, right? Because all of this template will be shifted up. There'll be different energies happening in different places, so it might not work. Now, depending on what the actual instruments are, like if it's a contrabass and a flute, maybe this will be okay because the sort of overall timbral shapes will be quite different. But if you have a trumpet and an oboe, perhaps those are going to be not, or I should say, if a trumpet is playing different notes, it might find all of those different notes to be different templates.
Nice.
Yeah. This is why it works really well for drum sounds, because that snare is going to be in the same spot every time. That kick is going to be in the same spot every time. Yeah. Another thing you can do is you can do the buff NMF decomposition process on separate buffers, so it doesn't have to be the sounds are always in the same buffer together. You could do a decomposition on one buffer, get a basis that is useful from that, do decomposition on a different buffer, get a basis that is useful from that, and then you can combine those into one buffer that then is passed to NMF filter, and then do the filtering that way. So you sort of collect those bases strategically, separately, and then do the filtering process. That might be a good way of going about it.
Thank you. That's
good. It's very powerful and also tricky in those ways. People sometimes reach for this when they're thinking about different instruments, and basically they're asking a classification question. And I always say, well, if you're asking a classification question, you should go to the classifier. That's going to be a more useful, applicable thing. This is sort of a very specific application. So, a confusion that happens sometimes. Other questions?
I have a question.
Please.
What is Max typically used for? So machine learning with instrumental production, or what makes it use this software?
So Max is used for all sorts of synthesis, sound design, sample manipulation, often in a more sort of a way in which a user maybe can't do what they want to do in a DAW or in a tool that's maybe more let's say off the shelf or something, because Max is really a programming environment. It's made for like almost like writing code, right? You're programming a algorithm to do something very specific that you would want to do that maybe isn't applicable in a different tool. So yeah, it's used for all sorts of sound design, synthesis, MIDI manipulations, sort of how it originally started many
Doing
years
weird things
ago.
with data.
Sorry?
Doing weird things with data.
It also has plugins to like, you can like do video stuff in it using a part of the software called Jitter. You can like send out information to control lighting instruments. It's like a very multimedia programming environment space.
I have kind of a question to piggyback off of that. Like, have you because I know that Max can be used with Ableton via Max for Live, and I'm wondering if you've seen people create plugins using FluCoMa to work within a more mainstream DAW.
Yeah, totally. So there's a lot of Max for Live instruments that incorporate FluCoMa. There's one made by Rodrigo Constanzo called CC Combine that is sort of a concatenative synthesis thing that happens in Max. And he has a bunch that are, he's made a bunch of Max for Live instruments, and many of them that involve FluCoMa. He also has a sort of subset of FluCoMa, or an extension of FluCoMa called SP Tools that's for Max, but it's sort of, he makes things a little more intuitive or user-friendly than FluCoMa can be, so it's a good thing to check out. Yeah, and also there's there's more for sure. So there's more Max for Live objects.
Another question.
Yeah.
Is it fair to say that the synthesis or filtering aspects of FluCoMa can be used with audio in or large files, or there's no scale issues in that regard? As opposed to buffer.
So yeah, there's not really an issue there. I mean, it tends to be the sort of things people do with it tend to like live inside of Max, right, or SuperCollider or whatever. So it tends to be things that live inside of that software already and sort of are already possible in there. But maybe there's been times when you are using Max or one is using Max and like it starts to like glitch out a little bit because your CPU is spiking, and so that sort of thing happens with FluCoMa too. But it's usually for the same reason, that you're sort of like trying to do too much and Max is freaking out. With FluCoMa, I mean, there has been people make data sets with tens of thousands of data points, and then we'll train a neural network with that. And that training takes longer, of course, because it's more data. And so sometimes that can be like, can that, like it's like on the edge of what Max can handle or what FluCoMa and Max can handle. And so if that's the case, sometimes I'll direct people to using Python to do the training, where you have a little bit more sort of stability or a little more, it's like a little more made for that, where Max is made for like, I don't know,
It's on
something.
the analysis side, not really on the
Exactly.
filtering, yeah.
Exactly. And then once they do some training in Python, then they can bring that trained model back into FluCoMa and then apply it in real time. And so sort of that workflow is something that's sort of on the edge of what you're asking, but not really. I mean, it's when those problems creep up, it's usually just because, like it's a laptop and sort of it's freaking out, just like Max might freak out if you are asking it to do too many fast Fourier transforms at once or something.
Yeah, no, thank you. That's,
Yeah.
That distinction is exactly what I was looking for.
Other questions?
I guess, just bigger
Yeah.
picture like that, in terms of tools. Is there anything you can say about the differences in the kind of integrations with FluCoMa between, say, Max, SuperCollider, and PD?
It's a good question. So we've tried to make it as consistent as possible.
Yeah.
Like the name of the objects, the arguments, the methods, it's all because number one, it makes the supporting the toolkit easier because the documentation is consistent. But also it's about like building community. So if we're here, we could have something where, you know, we got some SuperCollider users, some Max users, and we're sort of all hanging out in the same place, thinking about the same things, doing the same experiments. So that community aspect of it is very important. We try to make it as consistent as possible.
Yeah.
Of course, there are a few corners that could never be the same,
Sure.
but those are pretty small. Just really
Applications.
like about
yeah.
this many or so things that needed to be slightly different. Yeah. And the toolkit is based on the sklearn toolkit, which is a machine learning toolkit in Python. And so a lot of the same like sort of headings you'll see here are even like headings that we use, and the way they describe the different methods and the parameters they make available to users. And a lot of the interface design is based on this toolkit. So, because this was also designed to be as a sort of, let's say, entry point or sort of generally applicable, very useful set of tools, rather than having it be like the learning curve be too steep or the deep end be too soon. This is sort of the idea. And we very much see FluCoMa as being like, you know, very useful, and that's great, but also like if people are trying to do things that are sort of of a bigger scale, like, you know, let's help you find the other tool. Like, we're not trying to, we want it to be a gateway, you know.
Well, that makes sense because that's exactly what scikit-learn is for Python.
Totally.
So yeah.
Totally.
Is there a path, either existing or in discussion, to other platforms like Unity, for example, or for mobile development?
So for mobile, you could do pure data, which sort of is able, because of the way it compiles, right? It can sort of plop onto different systems a little more easily. I know people have compiled it for the Bella platform, the Bella board, which is like a microcontroller. It's like an Arduino kind of thing. It's some differences. Also, the code itself is really it is C++, right? So there is the core repo, which has all of the algorithms and such that are in FluCoMa, but agnostic of environment, so Max, Pure Data, or SuperCollider. And then those other repos suck up the C++ files from this repo and compile them accordingly, which is to say that the underlying like bones of FluCoMa are pretty environment agnostic. It is C++ code, and so one could certainly find ways of incorporating that into, you know, really anywhere that C++ can be compiled. There was some discussion at some point of making a, you know, interface or an interface to use FluCoMa inside of Open Frameworks, which is a C++ creative coding environment. That's usually for visuals and stuff, but it's sort of like a, you know, it's like a SuperCollider for visuals and C++. That's a weird, but you know what I mean. It's a creative coding environment for C++. And that there was some interesting progress that was made in that direction, and so the Unity thing would be sort of along these lines. But no, I don't think that it has like been totally realized.
Thanks.
Yeah. Other questions? We didn't look at it. We're not going to look at it right in the last minute. But the last patch that's in there is an example of the plotter. So this is going to, I'll just do a very quick demo. If you load in a folder of sounds, choose some analysis parameters, you can use an algorithm to plot all those sound slices in 2D space, and then navigate around those sound slices and sort of play with the different analysis vectors here, some different pre-processing, some different dimensionality reduction algorithms about how it gets plotted in two-dimensional space, and hear the results and sort of assess, like, you know, how the sounds turn out. That's a very brief overview, but I pointed out just to say that this is a whole nother part of FluCoMa that we didn't even look at, one that is used a ton, and is definitely worth playing with this patcher and investigating a little further, and finding those tutorials on the learn.flucoma.org, which are up there, and then doing more with that. So.
Is that similar to the Qatar interlude?
This is very similar to the cat art, yes. In fact, FluCoMa is in many ways a direct result of cat art. Like, cat art is cool, and the person who wrote the grant for FluCoMa said, cat art is cool, I wish I had more control over how cat art works, so I'm going to make FluCoMa so I can do something like cat art, but have more control over it.
Another integration question is OSC. Is there grammars or work that attempts to?
Yeah. So FluCoMa itself has no OSC, syntax or anything, because we leave that up to the creative coding environment. So if you're in Max, you'd use the OSC protocols or the OSC objects in Max, right? But it is absolutely part of using this stuff. In particular with like the neural network, right? You might want to have some wearable controller as the input to the neural network. You'd very likely send that over OSC, and then take that message, catch it in Max from the OSC object, and then feed it to the neural network, right, as the input.
Yeah,
so that
it's probably a domain question. Are there OSC grammars defined for the particular domains that you implement? That you support.
Yeah.
In your model.
Yeah. So there's OSC for Max, SuperCollider, and Pure Data for sure.
Yeah.
Ways to get OSC in and out of all of those. One of the softwares that FluCoMa was strongly influenced by is called the Wekinator, which is all based on OSC. It's all OSC in and out. You basically did everything via OSC with that. And that's an amazing tool, and has some features that even FluCoMa hasn't implemented yet, although we're slowly adding them. But one of the ideas with FluCoMa was like, wow, Wekinator is amazing. The OSC thing is a little cumbersome. What if we could bring those tools directly into Max so that we didn't have to do all the OSC flying, and we could really connect to the things a little more directly?
So there are grammars for OSC grammars for Wekinator?
Yeah.
Yeah. Okay, that's cool.
Yeah.
Thank you so much, Ted.
Yeah.
That was really awesome.
Great.
Yeah. And thank all of you for coming, and I hope you found this interesting. I think that this is such a cool tool, and Ted does such an amazing job of explaining it. So yeah, thank you for coming out and showing us all this and sharing your patches. Partly Ted promotion, partly self-promotion. If you want to hear what Ted does, part of what Ted does, are you going to use FluCoMa in your set?
Oh yeah.
Yeah. Tonight at the Hungry Brain at 9 p.m., the two of us are going to be playing a set, so if you want to come check it out. Ted makes amazing music in addition to being a fantastic teacher of this stuff. Yes, cool, resources. Check out these resources. I just want to also say Chicago Creative Machines has a website. It has a link to FluCoMa and the sort of learning tutorial page of FluCoMa, and it also has a ton of other, if you're interested in learning about other machine learning stuff, there's also a ton of other links there.
Yeah, it's awesome. I checked it out.
Yeah.
It's a good page. Great. Bye. See you tonight.
Yeah, thank you so much for coming. Come back the next 2 Sundays if you want to check out some video and sculpture and sound and fun, like trying to hack audio algorithms to make them unlistenable by the NSA. All kinds of crazy stuff. Come back the next couple weeks at 2 o'clock on Sundays. Yeah, thanks.